Let's get back to my earlier question about assertion synthesis. Who has technology like this? Who can explain that to us?
Can I?
Sure.
So again, if you think about it, the application-specific verification is benefiting from the fact that a lot of the specification is implicit in the problem that you're trying to solve, and the collateral input that you're giving to the process. So the CDC is benefiting from the SDC, and you have UPF and all of that coming into the process, and all of the assertions are implicit in the way that the RTL implementation idioms are being used in terms of what I put into my SDC, the UPF, and so on. So the application-oriented verification is, in a sense, doing assertion synthesis. Now, there is also a whole untapped gold mine, if you will, in terms of the simulation output, and correlating that to your verification concerns and extracting a meaningful hypothesis out of that is, I think, is sort of starting to see some play, and I think that there is a lot that you can get at the end of the day from there. So.
Yeah, I mean, I think you tried all the assertion synthesis stuff, and it kind of generally you may get one little gotcha that you hadn't thought about. But coming back to, we find in general the assertions that come out of it are not what we would call high-value assertions. They're not the ones that are going to help you do system-level debug or provide input for a formal tool that would be doing some higher-level reasoning. So like the kind of packaged XProp flows, it's definitely a technology application that's very useful as a push-button flow and can inform you. Again, it can inform you about something you hadn't really thought about your design. And in that sense, they're helpful. But it tends to be that the quality of the assertions that come out, they tend to be more automated and machine-oriented rather than something that the designers encapsulated that's meaningful, subsequently meaningful.
Actually, I think there's two meanings for assertion synthesis. Perhaps that's the problem. I mean, there's actual synthesizing properties, automatically. There is also the other aspect that is being done in the industry, and it's actually synthesizing assertions into the actual emulation into post-silicon validation too. So.
Oh yeah, that one. Yeah, we do that. Yeah. That's very useful.
Yes.
That's the basis for finger pointing.
Yes.
Is assertion synthesis into emulator.
So is there an earlier part or a later part of the design schedule where you would start applying these assertion synthesis tools? Can you start that as soon as the RTL starts being written, or does that happen later?
How do you guys do it?
We tend to do it, I'd say, when the RTL's stable, functionally complete and relatively stable, because it's something that it's at the moment an additive thing. You're kind of going, well, I think I've done most of what I thought I was going to do. Am I, the workflow application of it is, I think I've done everything I've thought of. Here's another look at things. Oops, and I think a lot of the going through a validation workflow, it always starts out, I wrote my test plan, I've executed my test plan, but I'm pretty certain there's lots of things that I didn't write in my original test plan. Assertion synthesis, we found, is one of the things that can inform effectively upgrading your test plan. And there are others. You talked about stimulus. Someone just talked about stimulus grading. You can also go look at the test bench that as it's executing and go, well, I wrote this test bench to execute my validation plan. And what did it actually do in terms of stimulus traversal, not in terms of testing? And you can kind of go, well, I can see that I'm not really getting a good shmoo of this event against that, against this event against another critical event in the design, like an interrupt.
Isn't that what functional coverage was supposed to solve for us?
No, that's not. Neither of these is functional coverage. Functional coverage is going, when I'm traversing a state space, I want the simulation, whether it's directed or whether it's random in some way, to hit a particular state space point in the design. What particularly I'm interested in. I'm not interested in, I'm not so much interested in whether the validation plan was executed. The teams are going to do that. What I'm interested in is whether their validation plan is complete or not. Because what kills me is an errata after I've delivered, not getting through the process. So I want to have some understanding about what it is I haven't done, as much as understanding what I have done. And there, things like assertion synthesis, stimulus grading have a role to play effectively in going, is my test plan as complete as it could be? Do I need to add more coverage points? Do I need to add more stimulus?
So I'm actually completely with John on that. That's actually, I think the quality of assertions that you get out of a simulation output are likely to be low quality assertions, but I think the role in terms of informing the designer or the verification engineer about what is not covered and so on is actually very valuable, because I think what it does is that in the past the verification engineer or the designer had to bring in his creativity in terms of coming up with the assertions. And now what this assertion synthesis is doing is in some sense giving you a list, and you have to review the list, it helps you inform, and it's sort of picking out of a list and synthesizing the list into something meaningful rather than doing everything from scratch, which I think is extremely valuable.
Yeah. I mean, interestingly, just coming back to that, the most valuable feedback mechanism we find is that essentially if you're going towards the end of a project, if you look at the bug rates by block, you basically then go, oh look, this block's got a high bug rate, drag the design and verification team in and do a scrub of their block and their test bench, and that's the one that informs you, and that will inform you where you need to focus your efforts. So, you know, all of these things are informing you how to get, when you're closed, that you have confidence that closure was closure.
So I think there are two, I agree to everything that was said on this. I think that there are two key times in the life cycle of the design that it's the assertion synthesis or any method which is not simulation based could contribute significantly. Either the early stage where, and the readiness question came before, it's ready when the designer thinks it's ready. It's the same time that the designer thinks that he could start run simulations. So at that point, if I can run something, you know, some assertion synthesis, some, you know, static tool that could get me to the first 10, 20% coverage, right, without doing anything, and I can use that coverage in my overall coverage plan or coverage tool, that has value. The other point, it's actually at the end of that cycle. So if I'm at a 95% coverage and I'm, you know, trying to get to these last, you know, 5%, if a tool can come in and tell me, okay, those are the points that are not covered, and I don't mind if it can even generate the assertions. I can either use them or write tests to or write smarter assertions to cover those points. That has a lot of value. So it's either the 10-20% at the beginning, or even the 3 to 5% at the end, which takes most of the time.
And I think back to the point of the panel, one of the things that we make great efforts to do is quite often in the past those validation reviews were only conducted by the validation team. What's absolutely critical is also to have the designers look at things like stimulus grading and all of these assertion things as well, because quite often you'll suddenly see a designer sat at a table and rapidly start emailing someone because he's just gone, oops, I forgot about that, and it's very, you know, that's what you're trying to catch. You're trying to catch the escapes that otherwise are going to go all the way through to, you know, post delivery. So by giving the designers even just the opportunity to sit down an hour and think about it and go, hey, did you know that the events on the interfaces can go all over the place like this, and this one can happen 50 cycles after the interrupt can actually come 50 cycles after the cache maintenance operation or the transaction on the bus. The designer may suddenly go, oh, actually when I wrote the specification I wasn't really thinking that could happen. So you also get feedback from some of this effectively validation environment and stimulus grading and coverage analysis back to the, not just to the test plan, but to the specification of the block. And that, from a critical escape issue is just as important as feeding back to your coverage plan. Make sure you feed back to the spec and the designers.
Well, so the spec is interesting because it's generally the traditional crossroads of where design and verification meet. They kind of start with a good quality spec. Do you guys have any recommendations for how the designers could craft high quality specs? Because that is really the earliest part where if they do that very well, it makes the verification job easier. They might be able to find some of those bugs a lot faster as well.
I mean, it's always a matter of company style, preference, design team. The main issue is the spec needs to be maintained. More escapes are caused generally because a well-meaning designer has done some PPA optimization across an interface, and that's thrown everything that the validation teams were assuming was true about the design out of the window.
Yeah, I think in addition to being maintained, I think they need to be actionable. I mean, I've seen too many specs that you can't clearly abstract out the verification objectives. In fact, I recently saw one spec that was thousands of pages long, and who had time to read it?
Sounds like something IEEE wrote then.
Well, so and again, I think they have to be actionable in the sense that you have to understand who is the customer of the spec. One of the customers is the verification team, and it's got to be actionable, something useful for them.
So to Harry's point, I think it has to be actionable in a number of ways. So one is that it has to be something you can incorporate in your simulation or in your formal analysis. It has to be simulatable. It has to be executable, and it also has to be executable in the opposite sense, which is that, that once I find a problem in my design, I need to be able to project it back onto the spec to show the designer in his sandbox basically what the problem is. And another aspect of being actionable is that I should be able to from the spec, if possible, I should be able to extract out abstractions that I can use in my simulation or my formal analysis, so that if I want, if the simulation or the formal analysis is not tractable, I can sort of parlay those abstractions into my analysis to simplify and to make it tractable down the line. So.
Yeah, in fact, that is one of the problems that I typically find is that the specs don't necessarily define the use cases, which is essentially these abstractions and then the verification team is just hunting for what are the use cases, and to your point, it's these unknown unknowns that create the problems.
One more item on the specs. So at least we're doing and also looking into using more high-level abstraction languages to describe the design and the verification models. I mentioned before system RDL, for example. That's what we use for registers. At some point of time, we figured out that we can't keep track. John was talking about maintaining the spec on the 30,000, 50,000 registers we have in a design. And but we can keep track on the code or we can write code that will generate that documentation, and that documentation is basically the reference for both the designers and the verification team. We actually can generate also the verification models and the RTL, but if you have a question about the usage, you go to that higher level abstraction or that system RDL file, and it's very it's human readable. You can see what's the access type of the register, which bits are reserved and things like that, without even going through the document. So that's just one aspect where we use higher level abstraction, and I believe the trend will be there also for other aspects. I mean, all the way to at some point describe the whole design and the whole test model through higher level languages.
So we've had an opportunity now to talk about sort of a grab bag of tool sets that designers can now use so that they can sort of bring the bug validation curve in a little bit so you can find some of those bugs earlier. We talked about X properties. We talked about CDC. Of course, we've always had lint there, and now we've got assertion synthesis. Obviously, providing good documentation is another one. Maybe someone, are there any other future technologies coming down the pipe that are going to add to that? None? Nobody?
Well, I want to add to your list. I mean, low power, the low power infrastructure verification, and more is built into it. I mean, as we add more sophisticated power, just 1 or 2 generations back, the designs had you can count the number of power domains, right? Today, you can't count them. I mean, there are hundreds, thousands. So. Power is one area that will grow more. DFT was mentioned before. Mm-hmm. So how much, and there's still a lot to do, how much can you use structural, formal techniques to anticipate what will be your DFT coverage, issues in DFT, uncontrollable, unobservable areas, fix them at the RTL, why wait, for the scan insertion itself. So those are two more.
I think instrumentation is going to be a big thing. Now, even the software designers or developers are asking for instrumentation on the die itself. So you've got quite a few customers of the design team saying, "Hey, we need to have all of the instrumentation we can get, just so we can do our own debug at the final, when you finally get the chip out."
Yeah, in fact, to Gary's point, it's at least what I'm seeing in terms of the growing challenges is the SoC integration versus the actual IP. That's pretty well understood, and then post-silicon validation is just going crazy in terms of the effort there. So to your point, instrumentation is important.
So are we looking at putting logic analyzers sort of on board?
Well, they do it today.
They do it today.
That's one of the problems, though, is there is no consistent way it's done. It becomes problematic when you start integrating multiple IPs from all over the place that have their own debug mechanisms.
So, so basically, there's baseline functionality, and then there are layers and layers on top of it to make the integration predictable and meet the specs. And so we're talking about power, DFT, and then going forward to make Moore's law extend. Are you going to have 3D geometries, and there'll be verification concerns that come out of that. And in terms of post-silicon validation, I think there is a role for static analysis to play there in terms of both figuring out how to instrument your chip so the triage becomes easier. And once you have something coming out of the monitors you have on a chip, to combine the analysis with some static analysis that you've already done on the RTL to figure out how to triage better. So I think this whole post-silicon validation space is going to become more and more important as the geometries get smaller and the field bugs are on the fringe of the functionality and timing and so on. And I think static analysis will have a significant role to play going forward at Predictors.
Well, so we've spent a lot of time talking about how the designers can contribute more. What about the other direction? What about verification techniques applying early in the architectural process? Has anybody studied any of that? I mean, we have at our disposal a simulation vehicle capable of operating at the transaction level with constraints and a knowledge of timing. Is there anybody out there trying to come up with a means to apply test bench skills to help validate what the architecture is going to look like?
Yeah, but I think every architect has their own way of doing that. Every architect of if we look at a CPU block or a GPU block, they will have a C model in their favorite way of writing.
A C model is one way.
Favorite way of writing C.
But can the verification process be implemented beforehand to simulate what the architecture is going to do in the future?
Yes, you can apply the verification environment to the C model. So certainly most process design we do, a verification environment applied to the model and applied to the RTL.
And a significant reused actually in the implementation too.
And it's reused on the RTL, yeah.
So basically what you're saying is that that verification and analysis are two separate concerns. And I don't think that they are separate concerns as much as they sort of feed on each other. So basically, the verification processes that you're going to put in place to exercise the various cases of of an SOC are going to help eventually in a better analysis of that architecture. And it's going to feed into the architectural decisions. And I would say that actually the verification and performance analysis and all of that, it starts at the architectural level. And it's not about doing the architecture first and then, I mean, you do the C model to do a better performance analysis. So verification is starting right at that very abstract level.
I think what we see, though, is at the moment there's very little reuse between those two worlds. Yeah. Mainly because of the timing aspect, the project timing aspects, and you don't want to burden the architects having to design too much verification stuff because they can just work in a little closed box environment. They don't need to worry about.
Yes, I would say that I think the community is sort of going for the holy grail where you have the architecture and you can synthesize from that. But I think that's a bit of a reach. I think if there is some sort of a middle ground where the architectural process, it sort of leads into a better articulation of the verification concerns and a sort of a forward propagation of those things down the line, I think that's a significant
and I think it works. We found it works well at the white box. You know, it has to be. So you know, you're looking at IP or an IP block or a subsystem as a black box. You can reuse verification collateral at the black box level relatively easy because it's usually a software payload or some sort of software oriented payload. Where it becomes very difficult, and I've not seen a great deal of success. I mean, it works, but there's no reusable success, is more at some of the SOC level where you're trying to do all these transaction environments, because it's just too hard to go between the RTL world and the performance modeling world. They're just too far apart.
And the bad news is we're going to have to do it because we got power problems. And the architect really has the levers that has the most impact over power.
Yep.
So it's a big hole in the flow. And keep in mind, the architects today are you know, it used to be an architect or maybe an architect and a secretary. But you know, today I'm seeing architects that have 200 guys working for them, doing the modeling. So they're going to have to take on some of the verification load, especially in the power end, in order to get these designs out.
Yeah, in some of our chips, it's also not just the power, but the latency and the bandwidth that you're getting out of the device too.
Yeah, and I agree. There is a very little reuse of those models in the actual you know, design pre-silicon testing, pre-silicon validation, and that's something that's actually missing. I mean, if we had, you know, good standardization and understanding of you know, how to go between, let's say, virtual platform environment to and TLM models and transactors at that level to pre-silicon verification, then we could basically, from the start, build it under those constraints and make sure that we can reuse them at the design level. It's being done today, but it's basically, you know, a lot of work involved. It's really manually.
Yeah, you have to question the ROI on it sometimes. You see back to your point, Gary, you see teams of large modeling people and you go, well, what actually did you get out of that you couldn't have got out of a guy stood in front of a whiteboard with a spreadsheet? You know, it's kind of some of the outputs from these environments and the verification collateral that comes out of them as well, because it's not reusable. You can put a lot of effort in for not a lot of result.
I know Derringer used to, before he retired, sadly, he complained all the time about making standards for these C-level models, because he had, at Intel, he once counted, and he had 64 different models for the same FIFO. And none of them played with each other, so you couldn't use any of them for any simulation.